Welcome to today's IChemE Safety Centre webinar on Pike River, Leadership, Culture and Design. My name is Trish Kerrin and I'm the Director of the IChemE Safety Centre. This webinar is meant to be interactive, so if you have any questions or comments you wish to share, please send them to me via the chat box and I'll endeavour to get to them as we move through the webinar. The purpose of today's webinar is to discuss the Pike River coal mine disaster on today, its 5th anniversary. The IChemE Safety Centre runs several webinars each year to share knowledge and learning amongst its members. So now let's talk about the incident that occurred at 3:45 p.m. on the 19th of November 2010 when the Pike River coal mine exploded with 31 workers inside the mine. 2 of those workers did manage to escape and the remaining 29 were trapped. Over the coming 9 days, there were several more explosions before the mine was eventually sealed and the 29 workers presumed dead. Coal mining's been taking place in New Zealand for around 130 years. During this time, some 172 workers have been killed in multiple fatality incidents, and more than 100 workers have died in individual fatality incidents in New Zealand coal mines. A commission of inquiry was set up to determine what occurred and what should be done to prevent future tragedies. This commission was the 12th such commission to examine New Zealand coal mining disasters. All attempts to recover the bodies of the trapped miners have now ceased as the mine is deemed too dangerous to enter. Let's look at the history of Pike River Mine. In 1982, the Pike River Coal Company formed. In 1998, it was acquired by New Zealand Oil and Gas Limited. Over the next several years, up to 2005, exploration was conducted and some permits obtained. In 2005, the decision was made to develop the Pike River site. In 2006, construction of the access roads commenced. In 2007, shares were offered publicly to raise funds to continue the construction of the mine. And in 2008, the mine was officially opened. By 2009, the development of the pit bottom had finally commenced. But in 2010, further capital was raised and, in fact, money borrowed, which increased the company's debt to continue to develop the mine. Following these delays and need for extra money, the CEO actually resigned in September 2010. In November 2010, the coal mine exploded. So today, we're going to look at this through the elements of leadership, culture and design, while exploring some of the decisions that were made. These areas are detailed in the Pike River Commission report, which is available as a download from the New Zealand government website. But what I want to do first is, looking at some of these signs, start looking at the leadership aspects that we saw in the mine development. So firstly, the company was under substantial pressure. By the time they'd decided to construct the roadways, they'd spent some $63 million on the initial development. They then actually went to the capital raising and raised a combined $143 million to complete the mine. This was raised in what we'll call year 1, and there were no delays anticipated at this point in time. Year 2 was anticipated to be further development of the mine, with the mining of approximately 24,000 tonnes projected. It was anticipated that by years 3 and 4, the mine would be cash positive and they would have started hydro mining in the 3rd year and would be producing substantial volumes of coal coming out of that mine. Focusing on the site leadership in particular at this point in time, the management team consisted of several people, but importantly, it actually lacked a ventilation engineer. This role was filled by the mine manager. However, the mine manager was busy being a mine manager, and the role of a ventilation engineer in an underground coal mine is a critical position in the organisation. So you can see that we have an organisation from a leadership perspective that is very focused on increasing revenues and starting to develop the mine so that it becomes cash positive as soon as possible, with a substantial investment for a small organisation. as well as a leadership team that wasn't complete and didn't have the required critical positions in it. So now I want to move on to some design aspects to explore next. Let's look at some of the decision making. So the decision to go with an underground mine rather than an open pit mine was based on two factors. One being that it was in an environmentally sensitive area, and the second that the coal seam itself was very, very deep. This made open pit mining uneconomical. Back in the 90s as well, when they started to think about the mine, it was decided that hydromining would be used. Hydromining is a method that generates higher productivity in mining. However, it also generates higher levels of methane liberation into the mine. So there is some concern with looking at hydromining being used in an underground coal mine in this particular area in this manner. Once that decision was made back in the 90s, it was never reviewed again. So that meant that even when they started to have some more information about the geological formation, they didn't consider changing the way that they were going to mine. So let's understand a little bit more about methane in the mine and the impact that has. So the coal seam that existed in Pike River had about 80 to 90% methane in it. And methane is flammable when mixed with air, between 5 to 15%. It's lighter than air as well. And the gases, when they're released from the mining activity and they go into the ventilation system, it is diluted, but it does pass through the flammable range at that point in time. From a human health perspective, it's also important to note that the exposure standard for methane over an 8-hour period is actually 0.1%. The actual content in terms of cubic metres of methane per tonne within the coal seam was actually measured at between 7 and 7.5. It was determined that this level of methane would be very difficult to control through ventilation alone. So pre-drainage was developed with an aim to reduce it to less than 3 cubic metres per tonne. And this concept actually then needed about 6 months of pre-draining to have any hope of reducing the methane content in the gas seam to that level. So pre-drainage is a concept that consists of drilling holes into the rock and allowing the methane to come out of the formation and vent away. That's because it's at a higher pressure than the atmospheric pressure. So the gas is slowly released and taken away through ventilation shaft because it's actually lighter than air, so it does float up. This view is a schematic view looking down on the mine from above. And you can see the dotted lines in here actually are the methane drainage line ideas that come through the mine entrance and the ventilation shaft. So when they started to construct the roadways, and we're now taking a look at a vertical slice through the mine, we can see that the construction first commenced with the development of the mine entrance. As they started to drill through and develop the mine entrance, they'd expected the rock to be 90% stone, which would self-support. However, it was found to be 80% poor rock, and because of this, the entrance required additional bolting to prevent cave-ins. It was anticipated that the development of the mine entrance would take about 6 months, but in fact it took 12 months and cost twice as much. They did eventually construct a mine entrance which was very well built in terms of being 5.5 metres wide and 4.5 metres high and bolted appropriately to maintain stability. But once we had the mine road constructed here, they then needed to look at how they were going to build the ventilation shaft. And there were 4 methods that they considered in building the ventilation shaft. The first method they considered is called a blind sink, and it was considered to be the safest method. It would have involved digging down from above. However, it would have been a very slow method and resulted in a lot of spoil that would have needed to have been removed from above the mine, and that would have required additional roadways to be built in this environmentally sensitive area. It would also require water treatment ponds and some other major infrastructure, and that would have required additional environmental approvals. So at the time, that was not considered feasible. The second method considered was LMAC mining. The concept here is that a mine cage is raised up where the workers drill and load explosives, blast away once they come safely out of that area, and then shore up the sides of the shaft as it is being built upwards. The spoil can then be removed through the main mine entrance roadway. This was actually a method recommended by the contractors and consultants for the particular soil type that they were dealing with. The main drawback of this method was that it wasn't going to be the fastest method to create a ventilation shaft, and they'd already lost 6 months on the construction of the road. So this method was rejected on the basis of the additional time it would take to do. Thirdly, they considered a second access path creating the ventilation shaft. This would have provided a secondary exit point in case of an emergency, and a number of people recommended this method because of that very reason, and it would be a safer method of drilling into the rock to create the ventilation. Unfortunately, this method would have been very slow, as happened with the first entrance, because it took twice as long and cost twice as much. This method was rejected on the basis of causing large delays and potentially significant costs. This leads us to our final fourth method, and the method that was actually chosen to create the ventilation shaft. This is called the raised bore, and it involved placing a machine at the top of the mine and drilling a small borehole into the cutting, and then pulling up through that hole the mechanical reamer. This was the fastest and cheapest option to drill the vent shaft. However, it was not suitable for the soft soil of the area, and as you are making this shaft, you cannot reinforce the sides until it is complete, which does place you at the risk of a cave-in. Nevertheless, this method was chosen as a method to use, despite the engineer that was brought in to undertake the work recommending against it due to the soil type. The equipment had already arrived on site, and it would have caused more delays and cost more money to have switched to a different method. So, even though the geotechnical engineer that was sent out to undertake the work recommended against doing it once he had core samples and produced a report, they looked then for what they could possibly do to try and make it a safer option to drill. What they discovered was the bottom 44 metres was not expected to be able to support itself, and that geotechnical engineer recommended using the LMAC mining method instead. So when they went to create the ventilation shaft, the geotechnical engineer gave some further advice to try and ensure the success of what was going on. He suggested they use 14-metre-long steel bolts to pin the bottom of the mine shaft to the harder sandstone above, that they lay a concrete tunnel so the vehicles could remove the extracted earth more quickly and not get bogged, and that they create a working bay a short distance from the shaft where they could place the spoil, reducing the time to clear the loads. However, the actions that were eventually taken was 8-metre-long steel bolts were used rather than the 14 metres recommended, because they were available on site and it wouldn't cost any time or any additional money to purchase the 14-metre-long bolts. They chose not to lay the concrete because that would take weeks, which would have caused a delay, and they chose not to create a working bay for the spoil, having confidence that they'd have enough time to excavate it. So they commenced the ventilation shaft using this method, and as the reamer was drawn up through the rock, there were some small rock falls. Before it was able to reach the top, the sides needed to be reinforced at the bottom of the mine, and that was not possible. They subsequently collapsed. This was because they removed the support of the stronger sandstone, and therefore the tunnel collapsed down. There ended up being a substantial gap of 12 metres across and 40 metres high. The top 70 metres of the shaft was actually able to be reinforced. To support the bottom of the shaft, they needed to actually fill it with concrete. So they ended up requiring 1,000 helicopter loads of concrete to be dropped through the top of the shaft to try and shore up the base. And then eventually the LMAC method was used to create a 2.5 diameter shaft that intersected with the main shaft. Now the main shaft was 4.2 metres and they had installed a 2.5 metre shaft to get to it. There was a plan to create a second 2.5 metre shaft, but that was put on hold due to cost. And this then potentially created a bottleneck in the mine ventilation capacity. And at the time they knew that, but they determined that it was unlikely to create any particular issues for them. Overall, this caused a further delay of 6 months because of the plugging of the bottom portion of the mine shaft and to drill the LMAC mine shaft. So by now, the mine is currently a year behind schedule. They've reached the second year where they were supposed to start to become profitable, and they've not yet developed the mine into any hydromining. During the second year, the company had to continue to raise capital and collected approximately another $140 million through both capital and loans. Given that the ventilation shaft was not complete, it was thought that more ventilation was required. So they drilled an extra slimline shaft of 6 inches to assist with the ventilation. To reduce the time and costs, they used the same drill pad that the 6-inch riser was used for the gas drainage. They couldn't drill with the methane coming from the 6-inch riser, so they shut it down while the slimline shaft was drilled. They sent the contracting crew home for 6 months while they did that. So this meant that although they were using that period to do the pre-drainage, they actually had to stop doing the pre-drainage because they were using the same drill pad. A further problem with the reduced gas drainage program was that the roadways started being built at the same time. And as these roadways were being built, they started to intersect with the drainage boreholes very shortly after they were drilled. The maximum concentration of methane gas goes through a borehole in its first few months, so this created problems based on frictional ignitions, the potential for large gas volumes at the face where they were drilling the roadways, and the potential for large releases of methane at the works. And this certainly affected the drainage lines as they continued to try and remove the methane. So as you can see, we've got drainage lines potentially going up here, and as they've started to drill the roadways, we start to see intersections appear. With each intersection, they either needed to block the borehole or to connect the pipework to take it to the riser. A 4-inch drain line was installed for drainage of the boreholes, and this was then connected to the 6-inch riser. So we have the 6-inch riser here and the 4-inch drain pipe here. As the roadways were developed, the mine was set to have a fresh air side, where the air flowed inwards, and an outwards air side as well. The outwards air would have higher levels of methane. This would flow to the main ventilation shaft and then be drawn upwards. Through this circuit, they were ensuring the dilution of methane for a safe working environment. At this point, I just want to talk about the concept of a stopping that's used in underground mines. And this is used to prevent airflow between the inward and the outward air. They're critical to stop air with higher levels of methane reaching the fresh air side, thereby just circulating methane through the mine. The stoppings are shown here as these little S's on the diagram. Now you can see the blue is representing the fresh air side coming in through the mine entrance, and the red represents the outwards air side. The stopping prevents that outwards air flowing into the inwards air. The stoppings need to have a pressure rating on them, and in the Pike River mine they were set to 14 kPa. So as the roadways developed, the 4-inch methane drainage line continued to be extended as the boreholes intersected the roadways. The line grew, and then more boreholes were added and drilled in and connected to the 4-inch line. The roadway development, however, was very slow progress. After 6 months, they were still working hard to develop the base infrastructure so they could even start hydromining. The methane lines continued to be extended. The cause of the slow roadway construction was because they were using continuous miners, a machine that continued to break down. And at the time, they were blaming the breakdowns on the operators and accusing them of not being able to use the miners correctly. However, when faced with the decision of which continuous mining machine to choose, they chose a unique prototype build because it was cheaper, rather than a commercially available and proven machine. They also had issues because of the soft soil that they were using, and they needed to install substantial amounts of roof supports as they went through the process of creating the mine roadways. As it continued to be created, they eventually installed what's called a fresh air base. This was a safe haven in the event of an emergency. However, if you look down to the bottom right of this diagram here in blue, we see the fresh air base. And the 4-inch methane drainage line runs straight through it. Once we got near the end of the 3rd year, there started to be some concerns about the methane drainage system. The system was undersized and therefore operating at quite high pressure. Also, there was a concern because of the fresh air base having the methane drainage line run through it. There were also frequent intersections of the boreholes that were used for the pre-drainage. These intersections created the risk of additional frictional ignitions as well as a potential for release of large gas volumes. The intersections also reduce the effectiveness of gas drainage, as the boreholes must have the pipe connected for them to continue to vent safely. You'll also see here that part of the drainage system also started to be installed over on the far left of the diagram in the clean air inwards system. So because we started to see several concerns raised around this, the company then decided to bring in an independent assessment of its drainage and ventilation systems. So the independent assessor came in, and immediately he had a lot of concerns about the stoppings not being sufficient to actually segregate the airflow. He noted that most of the stoppings looked temporary and that they were easily knocked over. In fact, he saw one that was just propped up by a piece of wood. They also appeared to be leaking around the sides, allowing methane to enter the fresh air side of the mine. It was noted that due to the high rise of the coal seam, the highest pressure within the gas drainage line is deeper as it goes into the mine. Therefore, it was creating restrictions as to what would flow out of the mine. At his first visit, he made a recommendation that within 3 months, the 4-inch line needed to be replaced by a 10-inch minimal diameter line to service the current and future needs. He also said that there needed to be further increase in the drainage and water control to improve the ability to maintain the ventilation in the mine. He then came back a month later, and during the second visit he became very concerned about an imminent intersection with a gas drainage line. You can see that up into the top left of the diagram here where the orange circle is. He believed the pressure was too high and intersecting the borehole at that pressure was very risky. Through discussions with the site, it was decided to free vent into the return airways. This is where the borehole is vented directly into the return airways, the red parts shown here, taking advantage of the main ventilation shaft. This raises the level of methane in the return airways, although it was monitored to ensure that it stayed below 1%. remembering 0.1% is the occupational exposure standard. Although this was intended to be a once-off activity, in the next month it was made standard practice to free vent almost all of the boreholes, raising the level of methane in the return airways even higher. At the third visit by the consultant, the roadworks were complete and the hydro extraction was about to begin. But there had been no upgrade to the gas drainage infrastructure, and the underground fan had not been commissioned. There was still just a small auxiliary fan at the top of the mine on the outside. They had also not determined the outburst threshold value, how much methane could be released. He described the core sampling as the single most important task that needed to be done. And insufficient ventilation for hydromining was a real concern, and that they not begin hydromining until the main fan was operational. So what I want to do now is move on to some of the cultural aspects that then played a part in this disaster as well. So, as part of the final push to achieve hydromining, the company senior management offered a bonus. If the first 1,000 tonne of coal can be extracted by hydromining, then an incentive would be paid. The incentive would reduce depending on how many weeks it took to achieve. The maximum payout available was $13,000. At the time that this was implemented, there was still no functional main fan in the mine. There was still only the 4-inch ventilation lines and certainly insufficient drainage, yet they commenced hydromining, which liberates substantial amounts of methane. So during this initial push, there was an incident where a stopping fell during a small roof collapse as part of the hydromining process, and this then further compromised the ventilation system. There were several incidents of high methane levels reported in the mine as well. The methane levels rose to greater than 5% where the mining was occurring, shutting off the equipment and stopping the mining. Remembering the exposure limit is 0.1%, but the flammable range starts at 5% as well. However, no action was taken to address these warning signs. 4 weeks into the hydromining bonus, 1,000 tonnes of coal was extracted, and a bonus of $10,000 was paid to all staff. It should be noted, though, that during weeks 1 and week 4 of this incentive program, there were 9 occasions where the methane levels exceeded 5% in the return airways. As soon as 1,000 tonnes of coal was extracted, it was decided to stop hydromining until the main fan was operational. Another near miss occurred just prior to the main fan being installed. The auxiliary fan, located above the main ventilation shaft, had a blade shear off. This shut the fan off completely, and the mine gassed out at greater than 5% methane. All personnel were evacuated, and it took nearly 2 days to restart the auxiliary fan and reventilate the mine at that point. So let's talk about the design aspects of the main fan being installed. So the main fan was due to come online at about 3 years and 6 months after the initial capital raising we spoke about earlier. During the tender process, the company did ask for the fan to be located on the surface, but given that it was a remote conservation area, this posed a lot of challenges. Fan location in a mountainous conservation land, access only by foot track or by helicopter, no direct surface electricity, and the weather conditions were often very, very harsh. Due to this, the 2 vendors that tendered proposed to put the fan underground. Now, this was the first time anywhere in the world a main fan would be located underground, and concerns were raised for both the above and the underground fan options. The company decided to go with the underground fan. So a hazard study was conducted, and it raised some of the following issues. There were concerns that the main fan could be destroyed by explosion. It could result in employee injury, business interruption, suffocation from methane in the mine. 2 of these risks were initially rated as unacceptable in the risk assessment but later revised to low risk in the light of varying controls, including the design and layout of the installation with a built-in explosion proofing, protection of the equipment by servicing and maintenance, design consideration of the doors, installation of blast panels to protect the surface fan, implemented detailed emergency response plans, requiring supervisors to monitor specific hazard processes and the installation of temperature and vibration sensing equipment, siting the fan in a solid rock house. However, it should be noted that the hazard study was never signed off due to a difference of opinion on the risks between the mine manager and the independent contractor that facilitated the hazard study. Importantly, though, many of the controls were not implemented, including the design and layout of the installation with built-in explosion proofing, the installation of sufficiently sized blast panels to protect the surface fan, and that the fan be sited in a solid rock house. So consequently, we see that we have the ventilation fan underground, unprotected sufficiently in a mine that produces high levels of methane. So in terms of what some of the key leadership learnings are, obviously we saw financial pressures versus the safety requirements. But interestingly, it cost more and it took longer when they kept going for short-term financial benefit rather than the safer option. From the design perspective, the pursuit of shortcuts in design to try and reduce the lead time to build the mine and the cost to build the mine, and the lack of suitable assessments and the rigour of those assessments prior to making significant design decisions. Lastly, the culture of the push for production without the necessary and required safety measures, and the total lack of action on the incidents they were having. So at this point in time, I'd actually like to ask a couple of poll questions. The first one I'd like to ask is, while this was certainly an extreme case, have you seen similar activities occur? And I'm starting to see the responses come in now. I have both yes and no responses to this question. Okay. I've got almost everyone voting now, so I'll actually close off the poll at that point in time and share those results with you. So we can actually see 73% saying yes and 27% saying no. So I think that's, whilst probably in my experience quite accurate, possibly quite a concerning result there, I think. Let's take a look at the next poll question. This one, have you experienced a situation where production targets disregarded safety requirements? Yet again, just a yes-no answer at this point. Okay, we're getting up there with almost everyone finished voting. Okay, so I'll close off this poll now as well with 92% of you actually voted in that one. So what we're seeing, 64% saying yes and 36% saying no. So that 64% is yet again, whilst probably anecdotally not that unusual a result, nonetheless, it is quite concerning a result. Okay. So let's then talk about, we're now 5 years on, what's actually changed? Well, around the world, there have been at least 6 coal mine explosions since the Pike River incident happened 5 years ago. Understandably, methane as well as coal dust continue to be a main hazard in coal mining underground, as we've seen. There's also been examples of open pit mines where there have been substantial fires as well. Importantly, in New Zealand, one of the things that we have seen, though, is the New Zealand government moving to a new legislative framework, because there were certainly findings that were adverse about the New Zealand legislative framework that led up to the Pike River Coal mine as well. So the New Zealand government have taken the initiative. They're adopting the Australian Harmonised Work Health and Safety Act. It is called the Health and Safety at Work Act, and it will come into force in April 2016, and that will see quite substantial changes around how mining, as well as other major hazard activities and indeed other activities, are actually undertaken in New Zealand. But in terms of some takeaways from today's webinar, so thinking about how leadership, design and culture impact on safety in your organisation. What are you seeing in your organisations? And how can you positively influence these particular areas if you think about that? One of the things that we see a lot of is bonus systems, the different remuneration packages that we see around in various different companies, and they can often have adverse impacts and drive unintended behaviours in organisations. So what sort of behaviours are your bonus systems driving in your organisation? And it's not necessary that we need to then change some of those bonus systems. It may be that we need to have other checks and balances in place to guard against the adverse outcomes that we might see if we purely just look at the bonus system itself. I think another really important outcome here is how expert opinions are valued. So we saw the situation here where a ventilation expert made several very critical and important recommendations, but they weren't taken on board. A risk expert conducted a risk assessment and in the end could not reach agreement with the site because the site management did not agree with the outcomes as they were. So a risk assessment was never signed off and completed. So I think from that perspective, there's just a couple of examples of where expert opinions were not necessarily valued. And we need to be very careful about that we need to be seeking the right opinions, but then also taking appropriate action with what we find. One last question for you all now. So let's look at the last question. And this is actually a little bit about the webinar. So has the information in this webinar challenged how you think about leadership, culture, or design? And you've got three answers here. You can have a yes, no, or a maybe. Okay, half done. Okay, so that's pretty much most people have come in and voted on that now. So what we've seen is 36% of you have said yes, 50% of you have said maybe, and 14% have said no. So I think that's an interesting spread. It was it's good to know how some of the information that we present may or may not be challenging you in what you're doing. So I think that's good information for me. Thank you. So this presentation, the details in it were based on two particular resources, one being the report of the Royal Commission, which was released in October 2012, and lastly a book by Rebecca McPhee, Tragedy at Pike River Mine, How and Why 29 Men Died. So they're both two interesting reads that you can get hold of to have a look. Also importantly, I'd like to acknowledge the work of Brett Maher from Process Safety Verification in the work that he did in supporting the development of the webinar, providing a lot of information based on these reference materials, and all of the images and graphics used were created by Process Safety Verification. Okay, now we're up to the questions and the comments section. Does anybody have any questions or comments they would like to raise? Okay, I've got... It's well known that reward structure influences behaviour. Any guidance on developing personnel's performance targets which balance safety and production? Okay, that's an interesting question. What I have seen recently, or it was actually released earlier in the year, is a review book that was produced by Andrew Hopkins and Sarah Maslin, and it's called Risky Rewards. It's a review of a range of different remuneration processes that are used throughout a range of industries. It was based on an industry survey. And it doesn't necessarily give you the answer as to, this is what you need to be doing versus another option. But what it does do is really highlight what some of the perverse outcomes may be from different areas and talks about some potential ways to get around them. So I would recommend that as potentially a good resource to take a look at and see whether there is anything you can be doing to help structure and plan your programs. From my personal experience, what I would suggest is, whilst it's very tempting and very easy to look at metrics that measure the number of a particular task done, you should also endeavour to have a measure in there somehow of the quality of the task, because otherwise you risk it being a tick box exercise and people just go along with it, do it because they have to, and don't actually really buy into the process. I think the other interesting area that I've done some work on in the past is around potentially, if you do have metrics in an organisation that are being used for performance-based pay structures, look at what adverse behaviours they might be producing and see if you can then come up with a countermeasure against that. So, for example, I was involved in a trucking organisation where we looked at how the contract drivers were paid. And so if you paid them per kilometre, then that actually potentially encouraged speeding so they could fit in more deliveries so they get to drive more. If you paid them by the hour, then you had to deal with whether they would go slow to drag out more pay. If you paid them by the litre delivered, yet again, if they get more deliveries in a day, are they pushing speed barriers? Are they pushing fatigue barriers to achieve those things? So we looked at how you could then implement other potential measures around, if it was a measure that would potentially increase their propensity to speed, how could you monitor and manage the speeding aspect of it as well? So it was around understanding what the perverse outcomes could be and then actively looking at monitoring those. Any other questions from anyone? Okay. I think I still just have the one question here. Any other questions or comments that anyone would like to share? No? You seem to be a quiet bunch today, but thank you very much for participating in the polls. Okay, so if there's nothing else coming through, then what I would like to do is wrap up this particular webinar. Certainly, I hope that you found it a very interesting and thought-provoking set of information and some useful thoughts that you can take back to your own organisation. This particular webinar is dedicated to the 29 miners who lost their lives in the Pike River Coal Mine 5 years ago and their families. The recording of this webinar will be stored on the IQME Safety Centre website for your future use. Thank you very much. And before I sign off, someone has just asked, will it be available online? Yes, it will. The webinar will be available online. So I will... Oh, I've got one last question. Do you have any information on what levels of methane are accepted in the mining industry? No, I can't specifically answer that question. I haven't actually looked in detail at what is typically acceptable, though we did see that there was some data earlier on in the webinar around the sort of directional levels that they were looking at, but I don't have any specific information on that. Okay, thank you very much for your attendance. Stay safe, and we'll talk to you again soon.